I'm Pete.
I'm Stephanie, and this is the Cool Part Show, our show all about cool, innovative 3D printed parts.
These valve components used to be crazy difficult to produce, made of machined parts that were stacked together and then assembled by brazing, soldering basically. It took a long time.
Now these parts are 3D printed all in one go. It's faster and very little redesign was needed.
Bonus, this is the best production part winner in our contest, the Cool Parts Showcase. That's all coming up right after this. The Cool Parts Show is brought to you by Carpenter Additive. When it comes to managing metal powder, there is no one-size-fits-all approach. Stick around after the episode to learn more. Welcome to the Cool Parts Show.
If you like the show, make sure to subscribe on YouTube. And as a reminder, you can also join our All Access newsletter for early access to videos like this and lots more content. Today on the show, we are looking at these parts. These are special parts because they were the best production part in our Cool Parts Showcase for 2023. So we have several parts on the table with us. These are all different variations, basically different same products in the same line. They are variable resistance trim stacks. These are industrial valve components, and they were produced, designed, submitted to us by Baker Hughes.
Baker Hughes, major manufacturer of high-end valves, among other industrial components, also a company that is leaning into additive manufacturing as a mode of production. As we're going to learn, this valve component it's a success for additive manufacturing, not just in terms of the geometry that 3D printing is able to realize. It's also a production success because of the way the Baker Hughes team is managing a high variability, high mix component and scaling up with that into production. But first, let's learn about this component, what it does.
So to tell us more about cavitation and how these trims work, I want to introduce Rebecca O'Donnell. She is a senior product engineer at Baker Hughes.
A variable resistant trim stack is basically a retainer that fits inside of a reciprocating valve. And its purpose is to alleviate cavitation within the valve. It's made with a series of stacks that break up the pressure drop throughout the flow of the fluid. And so it therefore eliminates cavitation within the valve itself. So cavitation is basically when a liquid drops below its vapor pressure, forming bubbles. Those bubbles then, when the pressure recovers, implode. And what happens with those bubbles when they implode is they experience a microjet against a metal boundary. And that can be particularly damaging to downstream pipe as well as inside of the valve. So at all costs, we try to avoid cavitation. And that's where the VRT or variable resistant trim comes into play. It eliminates the cavitation.
So we've said the name of this part a couple of times, variable resistance trim stack. The part is variable because these holes that you see change location as you move through the part from top to bottom. That is how the trim stack resists cavitation inside of the valve as part of the trim. And they refer to this as a stack because even though the ones that we have in front of us were all 3D printed as single pieces, previously when these parts were made, they would have literally been a stack of metal plates with holes drilled through them that were all brazed and assembled together.
For a picture of what that was like, the way these components used to be made, I want to bring in another voice. This is Mikhail Anisimov. He's additive manufacturing customer engagement leader.
These variable resistant trim components were conventionally manufactured as a stack of plates with drill holes that had to be brazed together and then machined to a final state, involving multiple vendors along the production cycle. The required coordination across all the steps was essential, and it regularly resulted in, in some delays because of the new vendors were added.
In each one of those manufacturing steps, you have a risk of something going wrong. Maybe something's machined out of tolerance, and it takes time to machine all the discs. Then when you send it out to a third party, you have an issue where, you're at the mercy of the third party supplier. The purpose of doing the 3D printing is to make sure that, we have total control of the part throughout, and we monitor the quality and the lead times.
So previously, these parts were made through a lot of assembly, and that was challenging, not just because there were multiple different parts that had to be joined together, but also because Baker Hughes was working with multiple different suppliers. They were all doing different parts of this process, and each of those steps took time. And so actually one of the big drivers behind looking at additive manufacturing for these components was reducing that lead time, trying to get these components faster.
Yeah, machining was done in one place, brazing was done someplace else. Even the machining, there were different operations, different stations, and so there were all of these different subcomponents or subassemblies moving from station to station, moving from supplier to supplier. Inevitably, there was some delay at every single stop. It was very difficult to schedule all of that. And as a result, Baker Hughes was stuck. They were stuck with having to quote long lead times to their customers for these parts. Now, by comparison, these components are made essentially all in one piece through additive manufacturing on machines located in Baker Hughes's own facility in Houston, Texas. So the company has taken control of the process, taken control of that lead time. That is a huge change.
Yeah, so a huge change in how these components are manufactured, from the timeline to where the manufacturing process steps happen, but actually not a huge change in terms of the design.
So with additive manufacturing, we are so accustomed to the 3D printed part being this organic form that looks very different from the components that it replaced. That's not the case with this. Like, this is a 3D printed part, but you look inside it and the logic of the stack configuration is still there. It still geometrically resembles the previous component. I want to bring in one more voice, because this is somebody who was instrumental in translating this part, the design of this part, into the current additive manufactured form. This is Rohan Buntfall, additive manufacturing design engineer.
When the valves group places an order for a new VRT with the additive group, the first thing we do is we take the models or the assembly and we consolidate the whole stack into a single body. We remove any vestigial assembly features such as alignment pin holes or plate markings that might be used to identify the individual plates. After we finalize the model, we then create the engineering drawings that detail the machining and post-processing requirements, and we put it through a review and release process in our product lifecycle management software, or our PLM system. Every AM part that comes to us has a unique additive part number and is revision controlled, and this is one of our requirements as an ISO certified facility.
So even though these valve components look pretty similar to the ones they replaced, there is a little bit of development work. There are some changes that have to be made to make these into something that can be produced through laser powder bed fusion.
Laser powder bed fusion. So let's talk about how these are made. The material is Inconel, nickel-based metal alloy. And these components come in a broad range of sizes, as you can see, from 1 inch in diameter to 12 inches in diameter.
And so every time Baker Hughes is faced with converting one size or configuration of these valve trims for additive manufacturing, there are some steps that they have to go through. So there is that process that Rohan described of looking for those vestigial features from assembly and removing them. But in some cases, they're actually looking for chances to preserve some of the features from the previous versions. So for instance, inside of these valve trims, there are these sort of slots, which would come from that sort of stacked structure in the conventional version. They wanted to maintain that, but these slots would be difficult to 3D print on certain angles of the part. And so you would need lots of little support structures in there, and then you would have to go in and remove all those little support structures. So their solution was to make the inner diameter of this part a little bit smaller, add a little bit of extra material, and for the places where it would be difficult or impossible to support those slots, what they do instead is print these little structures that look like airplane windows. So these are smaller holes that still allow for the powder to escape, but they don't need to be supported, because Baker Hughes knows that they are going to machine the internal diameter and they can remove that material and open up those slots after the fact.
So yeah, there are some straightforward post-processing steps, and the fact that they know post-processing is coming actually simplifies the design for 3D printing. There's cutoff. The parts are cut off the build plate with a bandsaw. There's depowdering, heat treating. This outer diameter is machined on a lathe, and then very precise machining related to this inner diameter, and it's that step actually that opens up those airplane windows.
So there are still plenty of steps in manufacturing this part, but the difference now is that almost all of them are taking place at Baker Hughes.
And previously, there were a lot more steps than that, and they were spread out across various different suppliers. And now all of that value is concentrated into one additive manufacturing cycle on one build plate. And in fact, it's better than that because all of that value for various different parts is concentrated into one cycle on one build plate. Because typically, Baker Hughes is now 3D printing multiple valve trims at once.
And so they've put a lot of effort into trying to capture all of this development, all of this value that they've put into these 3D printed parts. Once they have a good print file for any new valve trim that they're working on, they lock it down and they store it away so that the next time a customer needs exactly this valve trim, they can very easily and repeatably recreate it. They have a name for those files. They call them the golden build file.
Once the build strategy and slice files are finalized, then the build object then goes through a review and release process. And this freezes the build object within our PLM system to make sure that it cannot be edited or cannot be changed by anyone unless it goes through another revision process. We differentiate our standard productionized build within our PLM system by giving it a little golden icon, and we call it a golden build. So the production team will look for the golden build associated with the VRT part order that comes in, and they will grab the slice file from that golden build object and send it to the printer, and that maintains consistency and it minimizes the number of deviations that we might have in the process.
So the golden build file, I love that. Not every file is golden because the team at this facility, they're doing development, there are new processes being proven out. But every time a production build is performed successfully, the recipe for that success is captured in one of these golden files. And it's not just how to produce a part. Whenever a combination of parts, a particular build setup, whenever that's performed successfully, that becomes a golden file. And then a very different combination, when that's performed successfully, that's another golden file. And this is the way that Baker Hughes is capturing the library of knowledge, building up that library. This is the way they are achieving their short lead time, very responsive, high mix production process.
Yeah, so we've produced more than 70 VRTs to date from more than 20 unique designs, which is now a part of a large and digital inventory.
We see about a 70% reduction in lead time when it comes to 3D printing versus a traditional manufacturing method. And this is a positive thing for us because it reduces the lead time that we have normally had to use when one of these has been specified, either in a new valve or as a spare part. So we can get the part to the customer quickly.
If it's an emergency job, we can turn around the VRT in as little as 2 to 3 weeks. For VRTs that require design team work to work on the model, the engineering drawing, the build strategy, we've turned around VRTs in as little as 5 to 6 weeks.
So from 24 weeks down to just maybe 2 or 3 in the event of an emergency, like setting aside all of the benefits of assembly consolidation and reducing the risk of multiple components coming together, that time savings is a massive benefit for Baker Hughes and its customers. It can be so much more responsive and flexible to what customers need.
And look where that leaves them. All of the time improvement that they've won by simplifying manufacturing, by bringing it in-house, they've got that. The lead time improvement from additive manufacturing, they're there. So now, Baker Hughes is free to begin playing with the design, see what the new possibilities are because they're using additive manufacturing, and there is no one they have to coordinate with.
All right, I think we got this.
Take it away.
These are variable resistance trim stacks. These are components that go inside of valves to resist cavitation. They are produced by Baker Hughes, and these 3D printed versions are a replacement for the way that these components used to be made by assembling lots of different stacks of metal together and brazing them. It was a process that had a lot of steps, involved a lot of suppliers, and it took a long time. Now they are able to 3D print each of these trim stacks together as one piece.
There is some post-processing involved in making these components, but essentially these parts are now produced in one piece, in one build through additive manufacturing, actually produced multiple trim stacks per build in additive manufacturing. There is a lot of variation in the product line for these variable resistance trim stacks. For Baker Hughes, each valve project is essentially a custom build, but the Baker Hughes team is turning it into a repeatable production process.
Now that Baker Hughes has this system in place, they can very reliably and pretty quickly recreate any of these trim stacks that they have developed for additive manufacturing. The real win here is lead time. These parts used to take 24 weeks to source on average, and now they can produce them in just a couple of weeks when they need to.
If you enjoyed this episode, we have more from Baker Hughes about their production system, how it works. You heard from Rohan in this episode. Our All Access subscribers get to hear him talk more about the golden build file and how a build file becomes golden. You can subscribe to All Access too. It's easy, it's free, thecoolpartsshow.com/allaccess.
And again, this is the winner of the production category for the Cool Parts Showcase in 2023. We will have upcoming episodes about the winners in the other two categories, Bespoke and Proof of Concept. So make sure to subscribe to the show on YouTube to get notified about those episodes, or again, sign up for All Access to be the first to know.
If you have a cool part you want to share, maybe pitch it for a future episode, or even if you just like the show, email us, coolparts@additivemanufacturing.media.
Thanks for watching.
This episode's brought to you by Carpenter Additive. We're past the point of not knowing how to qualify metal 3D printed parts. We know, it's just that different end users of those parts have different qualification requirements. Additive manufacturing service providers have to navigate that, and Carpenter Additive has to think about that in tailoring powder management solutions.
Our customers typically will have, if they are a service provider, they will have a series of end user customers who may be, say, OEMs in the aerospace world. And each of them has a fairly large team of engineers who've been doing this for decades or more and have developed all these standards, regulations, paperwork. So it is certainly a challenge to thread the needle between all of these different requirements. We start really high level, we walk on the shop floor, we ask them about, okay, source to sink, how do you bring in the materials, goods in, send that material to each of the systems, and then what we're really interested in is how do they reuse that material. So what we do is called a value stream map. Pretty often that leads to a series of things that were either overlooked or hadn't really boiled up to the surface yet in terms of things that are potential risks or potential challenges or inefficiencies that exist. A lot of the customers we work with, especially in the more regulated industries such as space or medical or aerospace, have already been through those early learning stages. They've put 5+ years into this. They've done the product design and the design for additive manufacturing. And now they're starting to reach some of the more finicky problems that you get when you're at the scale of maybe 5-10 machines. You're running different materials simultaneously, you're doing different programs. Right, we get to take the best from the medical field and the aerospace field. We understand the specifications and the standards that exist in each of those fields, and we can sort of take the best elements of those and customize that to our customers.